Okay, my name is Viktor. I am here to explain the heat transfer value and to say something more about calculations in heat transfer in conductivity through different constructions. I am engineer of building engineer, and I also worked several years as a energy assistant. Have also a stand for the energy labels, so that I can evaluate a whole building, how well it is regarding to heat performance. So that is background that I can tell you something more about it. To start with the calculation and to say what is our goal is to be able actually to check this software like Ubacus is, a little bit to have an idea how it works behind, what is the background of the software, because yeah, different, we can play with it, but we can study it, but best is that we can at least have a rough eye on how it works in this calculation, because it's very simple calculation. This is first thing to say, and secondly, the other softwares which you maybe need should work similarly, and you should be able to check it as a, or make a simple calculation somewhere outside when client asks you how thick insulation you should add to get a passive house insulation. So heat transfer value about 0.1 for wall. So you may be able to immediately calculate him on paper how much insulation you should add to be passive in this insulation thing. Yeah. So you already had some value, the construction of the wall, if I saw it correctly, and maybe I can just quickly open it and share it also to point at the value we are speaking here about. So I'm opening now Ubacus, and I will share it also with you as Herbert did. I have already saved constructions, so it should be very quick. Count. It was some time I was not here, and it says me that I should pay something. Saved constructions, it's not here. Open, yes, here it is.
But you didn't share the screen.
Yeah, no, but, still nothing to see. Open, it doesn't work. Well, doesn't matter. I can share with you something else, and this will be a whiteboard, and we just start with the calculation right away.
I can show afterwards the Ubacus, yes.
Share screen. I'm sharing a whiteboard right now. So you should see just empty blank white paper. I will choose nice color, and I'll type U and heat transfer coefficient, which is in units of watts per meter square times Kelvin, and question mark. This is today's topic. So how to get it? You had in Ubacus some number. Do you remember what was the number for straw bale war for a U value?
Everybody.
Roughly. It's a question now to everybody.
So the lambda value is asked.
No. No, it was It was now a question for U value, and I just wanted to have
the U value.
imagination if people know what value we are speaking about. So does anybody just roughly what was the value for a Strobel wall? This
0.134. What we did
0.134
with clay plaster and lime plaster.
Good. Yes, this is roughly correct value, and we will calculate how to approach it. Let's draw our wall again. I'll take drawing tool. Okay, this is not straight, very nice straight wall. So again,
it's organic.
Yeah.
And please take a paper and draw it by yourself. Yeah, so you will follow what Viktor shows you and calculate it by hand now.
Yeah, we have simple few layers of our wall. This is our clay plaster layer. Then we have our Strobel, thicker, and then again our plaster. This time clay plaster again for just for simplicity. Yes. So this is yellow, pink, Strobel here, and the red layers is clay plaster. These, I will just mark also a letter C stands for clay, S stands for straw, and again C is a clay. It's clear. And our heat goes from left side, which is interior, and now maybe different color, green color, to right side, which is exterior. So it is a linear heat transfer conductivity, or I mean in the it's in solids and in one dimensional for simplicity. How it is, this is only calculation in, let's say, 1 point, one line going through a wall. It's a linear thing. This we can see also in coefficient lambda. So lambda, which has units of watts meter times Kelvin. It's only a meter here without, so it's linear. So it stands for the ability of any material. So it's different for all materials to conduct, to lead a heat. Yeah. So how much energy, how much in watts, how much energy goes through 1 meter, let's say, of wall in linear dimension, for that the change of temperature is 1 Kelvin.
And 1 Kelvin is 1 degree.
Yes, exactly. It's the same as Celsius, but then we speak about change of, in physics generally, when we speak about change of temperature, we speak about in kelvins. But there should be the same. It should be the same meaning when you write, instead of Kelvin, and you write Celsius, but you never see it in physics. So it's Kelvin. And this value is different for different materials. The lower it is, the better. It means the lower, the better insulating properties the material has. So for straw, do you have an idea what it is, the value for straw? for lambda, what is the most common used value? Because you can meet also different values when you search everywhere, whenever.
0.15.
0.15.
Zeros,
No, this is a little bit too big. The one is not there, so it starts with 0. That was correct. Point. 0 point, and there was if I heard well, you said Mike 1.
0.15.
No.
No, it's not 1.
The U value.
Yeah, now we speak about the lambda, now we speak about lambda, value for the material. So this is a property of every material. U value is the value of a construction which is composed of more materials of different lambda. Yeah, so we speak now about lambda. This is an ability of conduct heat. Yeah, so this is about 0.52 of the units which are above.
50, it's now 50.
Yeah, let's say 50 according to Dirk Schama and his research, it's 0.52, 0.052.
In Austria, it's 50, and in Germany, it's now 49, 0049. Yeah.
Yeah, you may show after that the poster of this Dirk Schama, how they were measuring and getting to this value. I think it's really interesting, and for me it was striking to decide to actually to go for this Strobel area at all, because this is very good value. Imagine that normal styrofoam EPS lambda of styrofoam is about, for example, 0.4. For some Steiko protects other insulating materials, let's say Steiko protect, it has for example 0.55, so it's somewhere in the same range, very similar to normal insulating, conventional insulating material. So wow, this is a huge opportunity to use a Strobel when you have right away insulation, like very good insulating material. So we have our lambda value for straw. This is here, so I can erase this. And for clay plaster, you have an idea how much it can be? It's probably, it's worse, but how much worse?
0.9.
Sorry, I didn't hear it.
Yuri?
0.9.
0.9. Yeah, it's a good tip. Actually, in some of the documents which we have, there's 0.9. Somewhere it's close to 1. Somewhere it's 0.6. Also depends on the amount of straw and so on. But 0.9 we can definitely use. So this will be our value that we will use, these two values. What else do we need? We need thickness of or distance, let's say, of our individual layers. So thickness of our clay plaster layer is, let's say, usually it's how much?
3 centimeters.
Let's say 3 centimeters. Yeah. And then we have Strobel, that's clear, that's 36. Yeah. And again, clay plaster, 3 centimeters. So this is always D. Now few terms, formulas. So we have our heat transfer. How to put into formula values we know that we get the heat transfer. As a big help is our units, because we have some units of lambda. We have the units of our distance, which is in meters, of course. So we should not forget that 3 centimeters are, for example, 0.03 meter. This is the distance for clay plaster. Distance for straw is 0.36 meters. It would be a wrong solution when you have if you would add centimeters. So now you can look again on the units. So we have meters, we have watt divided by meters times Kelvin, and in the end heat transfer value is watt divided by meter square times Kelvin. So what we need to do is this meter square here is different. So when we divide simply when we divide two numbers, at the end it's the right equation here. So this is a hint. So in formula, it's 1 divided by total. This R total, yeah, and now you will know already. R total is sum of individual resistances. This what our wall. So we have clay plaster, straw, and clay plaster again. So RC plus R straw plus RC again. And this individual RC, for example, is distance divided by lambda. Yeah. So here, when we do this distance divided by a lambda, I get meters divided by watt. Yeah, this is a little bit tricky in this easy in this easy platform for writing, because I have to now write brackets. What divided by
So what's the D stand? What's the D standing for? The distance.
The distance. This is this 3 centimeters and 36 centimeters.
Okay, the distance. Yeah.
So this at the end, the resistance should be the reciprocal value of what we have above. So it is meter square times Kelvin divided by watts. Yeah. Yes, if you follow, so this is the unit of R. Sum of these R is R total. And if I make 1 over this R total, I get back this blue value here, watt over meter square times Kelvin. This is, yeah, but important is that I do practically, this important practically is that I make calculation, for example, RC, which is now 0.03, so the distance divided by lambda, which is 0.9. So this would be RC. So somebody can tell me a number.
.0.033333.
Okay, periodical 0.333. It's very low thermal resistance, not a big effect on total resistance, but the second is much more important. Straw, which is 0.36 divided by 0.05, which is about 7.2.
Yep.
Yeah. So as you see from this, for example, that thermal resistance of this straw layer is much bigger than clay. What we can conclude from that is that clay doesn't have almost any effect on thermal quality of the wall, or very little. So our thought is sum of 0.033 plus 7.2 plus again 0.33, because this is again on the outside side. We have again 3 centimeters of clay plaster, and in total are dot.
There's a 0 missing at the second.
Thank you. I see. Thank you. So this is 0.266, let's say 0.2. So even the rounding of this number changed it almost more than the clay plaster itself, because we can say 0.27 or 7.3, let's say 27 of meters square times Kelvin watts. And when we do now, we want our U value, you get 1/7.27, which at the end is something what we wanted to get. That is number very similar to what we were speaking in complete beginning, 0.138 watts per meter square. Yeah, this was the simplest version of calculation. There is some more catches, how to say it, tricks behind what should be taken into account. Yeah. So, for example, just quick feedback. This very simple calculation, was it clear? So that we have layers of construction. It can be also a wooden board. It can be fine plaster, of course. There can be some external finish, whatever. This of course depends a calculation on lambda value of different material and on the thickness of individual layers and how to put it together. You have also accessible presentation when it is written again. But was it clear?
Yes.
Thank you. Because now we just add some questions. I will ask you for questions which may arise when you will calculate. For example, there are constructions which are not so simple as this one. For example, I will stop sharing of this whiteboard and share with you a detail of some construction in different presentation. Stop sharing, and I will share again something else. So should be sharing now a presentation. Yeah, for example, here, hope it is visible. Do you see a 5? Calculate the U value, a presentation.
Yep.
Yeah, picture. Okay. Here you see on this picture a detail of a wall with outside cladding, whatever. It's not important now. It's important. It's floor. And composition of this construction is there is some top layer of laminate floor, some expansion layer, which is against the noise, the impact noise. Then there is anhydride, like it could be a concrete or similar to concrete. Then there is some foil, also thermal insulation, of course. Then waterproofing, so bitumen felt of 4 millimeters. Then there is concrete slab underneath gravel, and then soil. So when you calculate a U value for such a floor on ground, which layers do you think that we take into account? So what's the opinion? What's your opinion about this? Yeah, sorry, this one.
Yeah, I guess all of them are except the soil.
You think except the soil, and why it should not be a soil? Just maybe stupid question, but it maybe reveal the core of this problem. Why not soil?
Then you have to measure the soil until the core of our planet.
Yeah, it's good. And what is tricky about measuring a lambda of soil? Yeah, it's about, it can be dry, it can be wet, it can be different, and everywhere that's true. But the deepest thing is the thing here is the wet or dry. Yeah, because what changes if it is wet? When you have, for example, a lot of rain, and there's water just below your concrete slab, the soil probably doesn't have so much insulation value, right? Yeah, because the water just flows, the heat takes a lot of energy with it, takes it away somewhere else, because there is actually it's something like convection. It's flow of the water, take it somewhere else. So we cannot take something which can be wet, in other words, yeah, because it doesn't have any insulating effect. So we are still not there. The soil is not calculated. And what else is not calculated then? Imagine that the water can be also higher in this gravel subbase, theoretically. When we speak about there should not be any water, so it should be somewhere where we have this waterproofing, isn't it? Yeah. So this general advice is to calculate only to our waterproofing layer, to our damp proof course, to our restriction where which is still dry, or which is still safely dry.
So, but
Yeah.
so you include the bitumen or without?
Yeah, bitumen is questionable because it doesn't have any effect anyway, because this rubber and it's very thin. So you could exclude also this and only calculate to the thermal insulation. Yeah. So this water, it's not necessary to have the bitumen, but there should not be a concrete, there should not be a gravel, and there should not be a soil. And if it has some effect, then it's on the safe side that in reality it will help you, but you should not calculate something which is in fact worse when it would be wet. Yeah.
You come to the exception, Viktor, that in case you don't have a waterproofing elastobit here and just a capillary breaking area.
Mm-hmm.
Yeah. Okay.
Yeah, that's true. The capillary breaking area is, if it is foam glass, then you of course calculate foam glass, because it's in the same time also thermal insulation. Yes, so this is good to mention. Thank you. But if it would be a foam glass, and from some reason underneath there is a gravel again, there you don't calculate the gravel, because it doesn't have any insulating effect anyway. But even though it's capillary breaking area, it can be very moist, and yeah, it's not added into its calculation. Yeah, so for this It's one example, and second example, something similar but maybe twisted. This is a green roof, and we have our slab, reinforced concrete slab, and our wall, and this green roof is composed of some plaster, concrete, and some bitumen again, but there is insulation. It's insulation after that, and then after there's the soil and some egg-grade foil, filtration layer, and substrate the soil again. So which layers do we count and which layers do we don't take? we cannot take. And it's the same principle, just to review it on, just to say it loud on
Yeah,
example.
I mean, it's only possible from that point where no water can go into.
Exactly, yeah. So we take from inside. When we go from inside, so from down, we can take, this time we take a concrete slab, even though it doesn't have big effect. Then we take these bitumen felts. Then there are some wedges of thermoinsulation, then the thermoinsulation itself, and then this real waterproofing, which in fact stops water from going into insulation. And this is where we stop. And we stop. Yeah, so this textile, like geotextile or egg-grade foil, this is this layer to accumulate water in, so it cannot have a big effect on thermal resistance. Then filtration layer and substrate, of course, not. So, okay.
Yep.
Yeah, okay. Thanks. There were 2 details. Another thing which is important, but not that important that it would ruin your calculation, but totally, but it's important to know that there's something like that exists. And this is, the calculation also varies if you calculate this heat transfer coefficient in the wall or on the roof or down to the floor, regarding to some additions. This addition is additional resistance inside and outside of this construction. And from physical point of view, of building physics, or what happens there is that on the surface of, for example, wall, there is certain layer of mixture of radiation, convection, and there also starts conduction. So there is certain layer which we add always on inside, on outside, with value of 0.13 Ri, and outside it's always the same, 0.04, like a little small resistance more, which is hard to measure for in each conditions. It's different all the time, but there are some, these numbers are empirically measured or gained, so we can always add them. We should always add them when we calculate. So if I would have our calculation again of our wall, when I stop share this and I start to have my whiteboard, I hope now, yeah, it is still here. Okay, so what I speak about now is, for example, in this pink color, I should add a layer here on inside, which has certain thermal resistance as well, and outside, which has certain resistance as well, because there's also a wind outside, which is all the time blowing along our wall. That's why it is much lower, this value, and this is our exterior, which is 0. No, we get this is not so convenient. E, and here I, and I should add this into my calculation of R total. So in pink color, so the more correct calculation here is that we have R total 0.30, so Ri plus the sum of what we had, which is 7.27 plus our Re, which is 0.13 plus 7.27 plus 0.04. You said it doesn't make a very big change of it, but formally it should be there to have it correctly.
Victor, I don't understand what the Ri and Re are physically.
Yeah, I do again. So 7.44. Physically, as you probably haven't spoken with Herbert about types of heat, what is the radiation heat, what is the convection in heat, what is the conduction. Maybe that's why you don't understand, and it's very hard. Actually, it's really hard to imagine it because it's on the micro, let's say, microstructure of the maybe in few millimeters outside of your face of the wall. When you imagine this few millimeters distance, there is some radiation heat which your wall heats, actually radiates out from the surface. There is also some movement of air, so convection.
Okay.
Again.
So, okay, but this is totally unrelated to the type of wall you're building. It could be a brick wall or.
Yes,
anything.
exactly. That's yeah, perfect,
okay. So
perfect remark. Yeah, thank you. This is for if it is wall, it's there whenever whatever material it is from built. Okay. It is this roof. It doesn't matter if there is a cladding down there or clay plaster or whatever. It's also there. It's on every construction edit. Yeah.
So that means 0.13 is always for the interior side and 0.04 from the outside.
Yes, in the case of wall, and 0.04 is also in case of roof, but 0.13, when I go back now to presentation, 0.13 is only for this, for wall, and for when you have this heat flow, this means for a wall, the heat flow is horizontal. Then you have roof, then the heat flow is vertical up. So for this value up, it is 0.10. Yeah, it's a little bit lower, this resistance. And when you have down, then you have some ceiling above the some street or if you have a maybe ventilated foundation with ventilated layer below, it's 0.17 this resistance value.
That got tested somehow, and now these numbers are given.
Yeah, it was measured and calculated, and now it's in standards like this.
Okay.
Ubaqus should calculate with it automatically. This is one of the reasons why you set up your, if it is wall or roof or floor, yeah, because it is a little different additions to that. Yeah, so maybe another thing which is can become more complicated or not so simple is, of course, we have some obstacles in our wall. It's not just straw, but we have there wooden posts, for instance. So maybe as it is in this example, you see this picture of a straw bale wall in the right up corner. I'm present. Make a bigger picture. Yes, here. Yeah. So, if, for example, here you have a section, horizontal section of wall where is 36 centimeters straw bale, but between the posts there is 94 centimeters, and then there is again 6 centimeter post, thick post. So it's a 6 by 36 post in every meter. Yeah. And what we have calculated until now was that the heat flow went in this layer of straw. Yeah, but then we have a part where the heat goes through this post, and it goes there with a big tendency, because from physical rule that this heat chooses the lowest resistance where it goes. It goes there, of course, in the similar way as through a straw. But how to get it now? How to get some complete value for our wall when we have a different regions? Let's say we have region there is straw, and then they have regions when there is wood. So we can do a second calculation, or do you have an idea? And you see here already some calculation. So do you have an idea how it could be done? Yeah, it's here. It's very simple case, so it can be done very easily. Yeah,
you use the wooden stand instead of the straw bale, and then you calculate the other U value.
Yes, exactly. So we calculate second U value where there is a wooden stand. There you see it's almost 3 times that big. So the wood in the way it's also thermal bridge, this wooden stand, because over there if it would be just a wooden stand, we wouldn't fulfill, for example, requirement for U value, because this minimum requirement is 0.3, and we have now in the wooden stand 0.33. So it's just to see this difference, and how we just we can put it together. It's simple. We can call it weighted average, for instance, that we have some portion of wall which is straw and some portion of the wall which is wood, and we make some weighted average from R. So this is what is done here. Let's imagine that we have 100 parts is one number 7.184, and 6 parts is number of woods is 3.030. So when we have 94 out of 100, we get this number, and when we calculate just portion of 6 out of 100 portions, 3.04, we get this number. And as these are giving 100%, these two has to also give 100%. So it's also called now like a rule of 3, or I don't know how it's named in German for this, that you calculate this in basic mathematics principle. Then you get some value R total, which is something in between. Yes, it's a little bit worse than straw, but because it was such a small portion, it's not 2 times, it's not 3 times worse, but it's just 0.015 worse than the straw. Yes. So we divide it on portions. If the wooden stand would be wider, it would be the portion here would be maybe 12 centimeters. This portion would be 12, and here would be 88. So total number would be worse again.
So in terms of insulation, it doesn't really matter whether you use 6x36 posts or two 6x12 posts. It doesn't make much difference.
Yeah, you're from point of total wall, it's not so much worse, that you are right, but there's another thing which we don't take into consideration here, and that is, for example, local temperature in that point. Yeah? Because there could be a bigger thermal bridge in this point of post, or if this maybe it's more obvious on the example when such a thin post could be from metal. It would be 1 centimeter metal post through whole wall. Of course, it wouldn't change that much the total U value, but it would cause decreasement of temperature maybe on 14 or 13 degrees exactly in the point of post.
At local, yeah.
Yes, and then it could be growth of mold and additional things going. So this is only one, but you're right that for a total U value, it doesn't change too much.
But it is better to use two 14x6 posts rather than one.
Yeah, it's better. It would be, maybe you can model it maybe with Ubacus, how it changes, because then it's for simple hand calculation, it starts to be then more complicated again. But in Ubacus, it can very quickly calculate this, and you can check how much it is better, but it is better, and it's even more important in the case when no such material with very high lambda goes through the wall. It's always better.
Yeah.
If you if you calculate that by hand, you had to do it like similar like Ubacus does it. It makes 3 layers, one layer 14 centimeter, the layer in between 8 centimeter, and then a third layer 14 centimeter again. And then you add these numbers which you get. So the 14 centimeter has included the wood, the 8 centimeter is just straw, and the 14 centimeter again is similar as the first 14 centimeter, including the wood.
Yeah, I mean, there are some more sophisticated hand calculation rules. You cannot make it until infinite. It is weighted average. In some point, doesn't refer to reality anymore. So, I mean, there are some special formulas for that. So maybe Ubacus problem, when you have this more complicated, I don't know, when there is, for example, some break, just to illustrate it, yes, when there is a break with a lot of these small cavities, and you have inside wool, for instance, you cannot just make these regions and make a weighted average, because the heat goes somewhere more quickly than to somewhere else, just because it's just physical rule. So you cannot, this is just simplified rule what we have here, very, very much simplified, and you cannot, for a very complicated structure, you cannot use it in the same way. Yeah, so this is for us, it's enough to know this, because these more complicated calculations, it's not necessary. For our, anyway, when you calculate U value by hand, where you want to know thickness of insulation you want to add, or thickness of insulation you need, you always should have some reserve. You should not calculate when your requirement is U value, I don't know, 0.15. So you should not have in bio calculation 0.15, but you should have 0.14 or something like that, because you can make some, there are some reality things which it's not included in the calculation always. So some extra portion to be on safe side. Yeah. So I think for this needs of our calculation, this amount of what you are able to explain by hand is actually enough. Yeah. To remember, so maybe just for a little repetition, I will share the calculation again. Yeah, so what when I put into frame that's important to remember is this equation of u. So u value 1 over r total, that r total is sum of these individual layers, that individual resistances are this distance divided by lambda, and lambda of basic materials you can always search, look for some in tables of national annexes, because sometimes if in different national annex, I mean, in annex for wood in Czech, for example, is different number than in national annex for Austria. So it seems that in Austria it's a better wood, or I don't know, different measurements.
Absolutely.
It grows slower, and that's why it's better.
No questionable.
Yeah, there's only equations, the two things you need to remember, and the other things you measure or know from the thickness of materials you have, or you search your lambda values. I think it's very interesting and important to make your mind to imagine what are different lambda values for different materials. Yeah, then you would come to picturing of the same when you, for example, calculate that you want to have the same insulation property, then a wall of stone or concrete should be several meters thick, some really nonsense number thick, that you get the same heat value. So it's really big, there are big differences in these properties of materials. So there will be a in presentation of Herbert some overview of it, I'm sure, and you will make your mind about it.
May I say that in the final feedback of this unit, you will upload this paper, and I hope that you have the same numbers on this paper as Viktor showed you now. So try to draw this, what Viktor shows you on the whiteboard on your paper as well. Yeah. Oder zu Deutsch, im Feedback werdet ihr diesen Zettel, den ihr da jetzt mitschreibt, beim Viktor hochladen. Dann bekommt ihr die Punkte für das Unit. Und ich hoffe, da steht dasselbe drauf, wie das, was euch der Viktor hier am Whiteboard. Weil ihr müsst es auch in der Prüfung können, diese Berechnung. Ja? Das ist ganz eine wichtige Berechnung. Back to you, Viktor.
Yeah, yeah, but it was 1 hour and this was what I prepared. So I thank you for your attention. I guess maybe there are some questions, or I don't know for how big extent you already know these things, because you go already half a year through the course and something was mentioned probably many times. So maybe you got some question about it, which is even older than from this 1 hour, regarding to these topics of lambda or heat transfer, or if Herbert may, yeah, or Herbert maybe could collect this question, and if at the end he has some, I can also answer at the end of this module, or I can answer by email to you. I don't know, Herbert. Okay, if it is something maybe from moisture also, yeah, which if there is some question, or from heat. Okay, Herbert, do you hear me?
I hear you, and it's okay. Yes. So are there any questions to these calculations now? Do you really, can you follow this calculation? Could you do it in a test if the question is calculate a U value for a wall which is 3 centimeter clay plaster, 36 centimeter straw, and you get the lambda values like on the first 3 lines on top, you get it. Do you think that you could make such a calculation by hand?
It's probably a stupid question, but I hope it's not. How do I determine whether it's upwards or downwards, or like on a roof, it's sidewise? I mean, it's not a real big difference, but this is something I don't know how to judge. I mean, I would say if I calculate from the basement up, I've got a floor, then, well, the exterior is probably the soil outside and the interior is the basement. And if, yeah, if I've got a ceiling, it's, well, probably the other way around. It's, this is what I am a bit confused right now.
Yeah, okay. Yeah, it's easy to answer. The interior is always where there you have a temperature of 20 degrees, then you imagine it's warm inside, and exterior is when you have colder cold temperature, it's outside. So when you have ceiling above your above the street, I don't, it's like a ceiling of some, or maybe better to say it's in that case floor. Yeah, of course, yes, floor above the basement. And then it is from inside to exterior, it's downwards. And when it's a wall, it's I think obvious. And regarding the roof, it's 45 degrees rule. So if it is from more than 45 degrees, the roof, for example, then it's like a wall. Then you calculate the horizontal number. But when it's, for example, flat roof or some roof which has slope up to 45 degrees, you calculate the heat transfer going up. Yeah. Okay,
so I consider 45 degrees as basically 90 degrees.
Yes, if it's 46, it's like 90. Yeah, exactly.
Okay.
Yeah, or 45. Yeah, it doesn't matter. Yeah, 45.
And I don't have to consider angles because that would make things probably much too complicated, because it's not that much of a difference. It's just this thing of, okay, thanks.
Exactly. Okay, thank you for the question. It's good to repeat such, such things which may be obvious for me, but it's a completely good question. It's really now understandable. Yeah, of course, in reality, you have some also some gaps in where there's a clay plaster, maybe deeper in the straw bale than 3 centimeters, but that's why also you have to be on safe side and to calculate maybe the heat transfer with some reserve of, I don't know, 10% lower than required, because in reality it can be a little bit worse. It's often in reality worse than in calculation. Yeah. It should be also, this is value of straw bale, lambda value of straw bale measured with 20% of addition by safe addition, that it can be also, it is natural material, so it's 20% worse, this number 0.052 then it was measured. So there is already some safety addition, safety factor, let's say. So some real measured values were even lower, like 0.04. So it's really good. Here it's always good to say that it depends on the direction of fibers, and because still I can see straw bale buildings which are built straw bale in direction that the stalks are going in direction of heat flow. Yeah, so when you imagine the straw bale and this size of 49 centimeters, that it's flat, so laying flat, that it's much worse lambda. The lambda value of this straw bale laying flat is maybe 0.08, so almost double. So it's maybe clear in the wall, but in the roof also it should be also perpendicular to the heat flow. So it should be also 36 centimeters. And 4.
Yeah. Victor, I have another question to that. I could show and share the screen with Ubacus and the same wall you calculated now. There are some results on this side, and would it be possible that you just interpret from your position the numbers which you see here?
Okay.
About the U value, the dew point, and moisture, these things, yeah. Can we do that?
Yeah, sure.
So I will share the screen, and I have the same construction as you see, 30 millimeter clay plaster, the straw bale with 360 millimeter, and again a clay plaster. Now, the usual thing which you see when you make it in Ubacus is you have water here, condensation. The U value is exactly what you calculated with the additions of these transitions, 0.134. So it's naturally a house which we could build, a wall which we could build according to the building law, to the standards. And here we have the dew point, 0.90 kilogram per square meter. So this is always the question, how you would interpret such a number here. The red bar, especially for the dew point.
There are two things I would comment about it. Yeah. The first thing is the one which you maybe mentioned as well, and this is that we speak here about diffusion of water vapor. The general principles for design of building constructions are that we need to have much bigger diffusion resistance on inside and lower diffusion resistance outside, so that water doesn't condense here. And here with the same layer inside and outside, we have the same resistance outside and inside. And this is why, from point of view of this diffusion review, let's say, it doesn't work very well here. But it's important to say that it doesn't take other phenomena which are there into account, which are happening in the real structure. First phenomenon is a phenomenon of capillarity, which is completely different means how the water is transported in the wall. So this diffusion is really very long process, which works on microstructure of part of these materials. And capillarity is something which transports much bigger amount of water. It's in channels between in these bubbles of material which are connected. Similarly, as I don't know if you have already explained the phenomenon of capillarity, but similarly, as tree is sucking its juice from soil, then the clay plaster, for example, is sucking water from every material, from wood, from straw, from other materials which are wet, and it sucks it and it transports it outside. And this is not taken account here, so it's more than for me, it's almost sure that this water which is transported there, and it's not so much of water, like almost 0.9 liters or meters squared. It's not so small, but it sucks it from the straw and transports it outside in very short time, and then it can dry out again. So this is what it doesn't tell you, the subaccus. So in fact, this is warning, this drops of water is warning that from point of view diffusion doesn't work, but the subaccus itself has it in explanation, and you can read it by yourself in hints, or in, I think it would be in hints, or isn't it, or some in explanation of how the software works, that it doesn't take into account these phenomena. And the second word, second thing I wanted to say is that some in standards, for example, in different standards have different approaches. You can set up here this 2D finite element method, which Herbert has it there, but you can also set up it in according to these German standards, some other actual version 2018, for example. And there it says that you need to have some more, I mean, yeah, let's say, in other words, up to some amount of water which is condensed, it's still okay if the overall 1 year evaluation is positive. It means that after a season, after winter season, you may have some dew there, but still it will evaporate in the rest of the year, or maybe in the spring, during first month of spring, it would evaporate. So this is depending also on temperature outside. For example, here it's set up that -5, it's -5 degrees. And then you calculate this amount of water which condensed there during these cold months, you get to some amount, but then when spring comes and summer comes, you get some evaporation there, just with the same diffusion, but the same process, but naturally this dew will evaporate. And if after this 1 year cycle you have now no water there, it's still okay, such construction. So even some small amount of water there could be, according to standard, okay.
Okay,
yeah.
Thank you for this explanation. The next one is the humidity of the wood. It says here 0.0%. Can you interpret that?
Isn't it because there is no wood modeled?
Yes, you're right. Okay. So
but you have interesting. There is this Trocknung Dauser. This is the drying period, right? The 23 days, for example.
So we could add naturally here 60 millimeter by
still 0% there.
in a distance of 800 or whatever, something like that. Yeah. So, but it doesn't change the.
Yeah, it doesn't change. You're right. I'm not sure about this. You have to search.
Okay.
In these properties, but maybe what I was speaking about before is this Trocknung Dauer. Yeah, right. This is period, drying period. And this is something I was telling about, that this 0.82 kilograms, when conditions will change to better, that this diffusion works the other way around, then it would take 22 days until it's dry, this amount of water.
Yeah.
So it's not so much. Yeah.
And another question to the phase shift. Sometimes I read 12 hours is the best, because then at 2 o'clock in the night, you have still the right temperature, similar temperatures as during the day at 2 o'clock.
Yeah.
So what is if we have more? does it mean the temperature curve is different and more is bad or is more better?
And that's a really good question. Yeah. Yeah, I have the same rule which I learned that the 12 is good, but with these big densities of materials, we get to very large. I even had some construction of 24 hours there, and then it's.
So usually 24 hours means that if the next day is a cold day, cloudy day, the temperature still is in the right.
Yeah, but it could be also like that you have a warm day and then again warm day, and and then it would theoretically accumulate. No, so the thing is that in this sinusoid of amplitude, the peak should not meet, and this is why the 12 hours is there. So I would say the closer to this 12 period, the better. When you have the 18 hours and you have 24, it's also bad. Yeah, okay, 18.5 we can see it here. Yeah, so you see that you are somewhere on neutral point of this amplitude. So it's not easy to say if it is bad or if this definitely is worse than if it is 12 hours. I think ideally you should take always be closest to 12 hours or to be not or close to it.
Here in this graph, it says, okay, the inside temperature is leveled, so it doesn't change even if you have this 18.5 hours phase shift.
It's very very inflated and it doesn't change. If it will be very slim wall, just from OSB board, it has a very big capacity at all. Like I mean. Total or absolute number of thermal capacity is very big, so these changes of amplitude are very small, almost invisible. But if you have this wall which is not from straw bale, but maybe there is just OSB board and EPS and OSB board, it would be much more important. Yes, it would be then this amplitude much more important to design 12 hours than 18. Maybe here it's when I see it on the chart there, it's almost not important here in Strawberry because it's already such a big capacity that the change of temperature inside is not.
Let's say I have so this is outside, sorry. Inputs and metal inputs. So if we have on the inside wood instead of wood, for example, 30 millimeter wood on the inside, which is from the building physics, it's quite okay. But then we have
but there's still straw bale. So maybe you change straw bale for some conventional insulation.
So any kind of
EPS or
EPS
or wool. Yeah, it doesn't.
Mineral wool, let's say. Steinwolle. So now the phase shift is 12 hours instead of 18.
Yeah, and you see that this how it's in English, the capacity is now almost in yellow. It's much worse.
This one,
so theoretically, the change now we should see this change in the graph much better, much bigger. So if you try it.
So this is just a half. It was 80 kilojoule per square meter Kelvin before.
Yeah. So just you can go on this balance, or I don't know where it was here. Yeah. I see it's the blue line is now flowing much bigger.
A little bit curved,
a little bit curved. So it has bigger influence now when this, and this is but this is now an ideal when it's 12 hours. This peak of blue, which is a little bit goes to up, it balances this red line, which is a lot down, and that means that this it goes to the night, or when it's the lowest temperature, and it should not be a big problem. I think, in fact, this moving of temperatures, the blue line, in reality, can be much bigger than here. Here it's only 1 degree, and in fact, I think when you have very different change of temperatures, it can be bigger.
In this case, I would have a little bit more warm nights. Yeah. So.
Yeah. Yes.
But we're still talking about that we have like 20 degrees inside and -5 outside of the ambient.
Yeah.
For now, with this example.
Yes, you always have the 20 degrees and -5. Yeah,
you can try to put the -15. I don't know. Maybe it should be in the graph.
The phase shift doesn't change, but probably the heat curve, no, doesn't change. What will change is most probably the humidity.
Yeah, that is changed.
As in whatever example, you have a castle with really solid rocks, super thick. I don't know, the sun is coming in summer and they're heating up for weeks, and would be the phase shift some weeks until they cool down in winter or in autumn.
Yes, you can try it out. Yes, there's an example wall just made of stone or concrete or whatever. I mean, the phase shift will be less, but the storage capacity will be higher, much higher.
Okay. Yeah.
Yeah. Okay. I have to apologize. I will have to finish.
Yes.
So.
Thank you, Victor. I think there are no more questions. We will proceed with our unit.
Yeah, thank you for this discussion. It's always good to discuss it with different point of views again.
And the invitation of Victor, if there are any questions concerning to his presentation, just write it and I will forward it to Victor and he will answer it. Okay.
Thank you.
Thank you, Viktor.
Thank you, guys. I wish you a good start into building physics and enjoy it. So, bye.
Thank you, Victor.
Bye.
Bye.
So we already made a long phase and we need a phase shift of 8 minutes until 16:30, and then we do the last half hour, the presentation about heat transfer today until 5 o'clock. Okay.
You want to do that in German?
As you like.
I don't need to be here if you. I don't want to spoil everybody's party.
Yes, then we could do it in German, but tomorrow at 9 o'clock we have to do it in English because Aldo will be there. Yeah,
I will be there.
Yeah.
I'll see you tomorrow at 9 o'clock.
Bye-bye, Mike.
See you, Mike. Thank you.
Ladies.
Ciao.
Have a good one.
Ciao.